So good morning everybody. Today we are going to discuss the helical spring test. The test can be of tensile test or compressive test on a helical spring. So helical spring is also called as a coil spring. So it is a coil of wire, okay, twisted in a manner into a coil in the form of a coil. Okay, so it is called as a helical spring or a coil spring. Now, the manufacturing of the coil spring is done by twisting a wire, a circular wire, okay, into a coil, and the coil spring or helical spring is manufactured in that manner. As the wire, the usual cross section of the wire is going to be circular or hollow circular cross section, and it has been twisted in this coil in the form of a coil in this as shown in the figure. Now, the coil springs, the important terminologies used or important parameters in the coil springs are the wire diameter. As I said, I am going to twist the wire into a coil, so the wire will have a diameter of d. So the cross section is circular cross section, so the diameter will be small d. And the mean diameter of the spring is of the entire spring is capital D, which is minimum. So mean diameter is this. The distance is nothing but the mean diameter. The mean diameter is nothing but the mean value of outer diameter plus the inner diameter. Okay, the mean value of these two values is going to be the mean diameter. So it is also called as the coil diameter. Okay, the coil diameter or the spring diameter or the mean diameter of the spring. And the number of turns of the spring is also another important parameter, which is represented by small n. So number of turns, okay, how many number of turns are there in the coil spring or in the coil is the number of turn parameter small n. Okay. So in the spring, the number of turn is 1, 2, 3, 4, 5, and 6. There are 6 turns in this coil spring. And as the spring is made of a material or metal, okay, so the material property of the spring which is considered, material property of the coil spring which is considered here are the shear modulus or modulus of rigidity, which is represented by capital G. Capital G. We also use this capital G or the modulus of rigidity value in torsional test experiment. I hope you remember it. So G is usually mentioned in the unit of Newton per meter square or Pascal or gigapascal, whereas the wire diameter will be mentioned either in millimeters or meter. As in here, the mean diameter of the spring is represented using millimeter or the meter. Okay. The other important parameters are the pitch distance, the coil angle or helix angle, and the free length of the spring. The free length of the spring is nothing but the total length of the spring, so which also includes the gap between the coils. So these are the gap between the coils. The gap between the coils also been considered. So that is the free length of the spring. Okay, but when we compress this entire spring, okay, in such a manner that the gap between the coils are zero, or there is no gap between the coils. Now the length of the spring is going to be the number of turns into the wire diameter. Okay, number of turns into the wire diameter is the uh, one of the this is the length of the spring after the spring is compressed in such a manner that there is no gap. So the diameter of the wire is D 1, 2, 3, 4, 5, 6. As I said, there are 6 number of turns. If I compress this entire thing will be closer to each other, and the total length of the spring is going to be 6 into D, or number of turns into D. Okay. But if I have a gap, okay, so the gap also been included, and that's the free length of the spring. Okay, so pitch is nothing but, okay, the gap between or the distance between the two successive coils or two successive turns. Okay, the first turn, the second turn to third turn, that gap is nothing but the pitch distance. So pitch distance is nothing but the radius of the coil plus radius of the coil plus the gap is the pitch distance, which is nothing but gap plus the diameter of the wire diameter. Okay, wire diameter is nothing but the pitch. Okay. The coil angle, or also called as helix angle, which is represented by alpha, okay, is nothing but the angle of the coil. the angle of the coil. So this is also another important parameter. So if you purchase a spring, okay, we look into the number of turns, the pitch distance, the mean diameter, the wire diameter, and the helix angle. Okay, that's another important parameter. Okay, so whenever you use a spring in any system, okay, this the single terminology used for the spring is called the spring constant or spring stiffness. So whenever you apply the spring in the system, and in that system, to calculate the performance, okay, the spring, okay, I won't be taking all this parameter and all. I just take a single parameter that is called a spring stiffness. Okay, that has been applied in the spring in the application, in any application. So spring stiffness or spring constant, so both the names are going to be representing the same parameter, which is K. So the unit for the spring stiffness or spring constant is Newton per meter or Newton per millimeter. Usually that will be the unit. So spring stiffness defines how stiff the spring is. Okay, how stiff the spring is. If the this value is more, K value is more, that means that the spring is more stiffer. And the K value is less, that means the spring is less stiffer. If it is more stiffer, that means that it cannot be deformed. You know that if a body is more stiffer, it cannot be deformed by applying any amount of force. But if the body is less stiffer, okay, the body can be easily deformed as and when needed by a small amount of force itself. So whenever the stiffness value is less, okay, the spring will be less stiffer. That means that by applying a small amount of force itself, I will be deforming the spring. Whereas if the stiffness value is more, okay, the spring will be more stiffer. That means that by applying a huge amount of force also, I will be getting less deformation or less displacement on the spring. The example of less stiffer spring, okay, less stiffer spring is springs used in a pen, as a springs used in a toy, okay, or nothing but less stiffer springs, which will be easily deformed by a small amount of force also. Whereas the example for a less stiffer spring is the spring used in a pen and a springs used in a toy. In those conditions, the stiffness is so less. uh, so these are the example for the less stiffer springs. So by applying a small amount of forces up, those springs will get easily deformed. So that's why it is called as a less stiffer springs. Okay, the stiffness will be so less. Okay. The example for high stiffer springs, okay, the springs with high stiffness value, okay, are springs used in automobile, car, bike, or ship, or train. Okay, the train suspension also use springs. So those conditions, so for each application we use high stiff springs. So in those conditions, the spring will never get easily deformed. Okay, it requires more amount of force to get deformed or get displaced. Okay, so those are the example of high stiffness springs. Now let us go into a problem. Okay. So I'm having a spring. One end of the spring is been fixed, and the other end apply a force. The force can be either a tensile force or a compressive force. If I apply a tensile force, okay, the spring will get expanded. If I apply a compressive force, the spring will get compressed. Okay. For a same stiffness spring, okay, if the same stiffness spring is being used and I apply a force, either a compressive or tensile force, it will have a same amount of deformation. Okay, either tensile or compression, it will have same amount of deformation. X value is the displacement or deformation of the spring, but the only difference is it will be the opposite direction. Okay, for a tensile force, it will be in the expansion direction, whereas in the compressive force, it will be the compressive direction. Okay, the negative direction. Okay, so stiffness of the spring, okay, can be, as I said, it is nothing but based on the application of force. Okay, how much it is be deformed. Okay, that's the definition of a stiffness of a spring. So that will be defined by a two parameter called force applied on the spring and the displacement of the spring. So spring stiffness is defined by force by displacement. So if I apply a force and the displacement is more, okay, if the displacement is more, that means that the stiffness is less. So it is a less stiffer spring. So it easily deformed. Okay, if the same amount of force is applied and the displacement is so less, okay, if the displacement is so less, the stiffness value will be more. That means that it is a more stiffer spring, okay, which is example can be used in automobile applications, car or bike. Okay, so this is a general formula to find the stiffness of a spring. So whenever I have a spring and I need to find the stiffness of a spring, I just apply a force and find out the displacement of the spring. By dividing those values, I can get the stiffness of the spring. Okay, for any unknown spring, okay, in new spring, I can able to find the stiffness by this formula. Now, to find the displacement of the spring, if the force and the stiffness of the spring is known, then this formula is this interchanging the values. So x is equal to F by K. So force by stiffness is nothing but the displacement of the displacement of spring. And if I know the stiffness and the displacement, I need to find the force applied on the spring. Then this is the formula. So just taking x to the other side. So F is equal to K into x. So by to find this force applied on the spring, so it is stiffness into the displacement. Okay. So let us this is have an application and let us find out whether it is correct or wrong. So let me take I'm taking a spring stiffness as 500 Newton per meter. So this is the spring stiffness. So I'm taking a spring of stiffness 500 Newton per meter, and I'm applying a force of 50 Newton. Now, based on this formula, so displacement is the only thing I don't know. So displacement is nothing but force by stiffness. So if I apply the formula, force by stiffness 50 by 500, I'll be getting a value of 0.1. The unit is meter because Newton by meter is nothing but meter. Newton will get cancelled. The unit become meters. So displacement is in terms of meter. So the value is 0.1 meters. Okay. So for a spring of stiffness 500 Newton per meter, if I apply a force of 50 Newton, the displacement is 0.1 meters. So let us check it out. Check it out in a simulator. So in the simulator for a single spring, okay, stiffness is taken to a value of so 500 Newton per meter is the stiffness I'm taking, and applying a force of 17 newtons. Sorry, applying a force of 15 newtons. So when I apply a force of 15 newtons, as you can see, it is 0.1 is the displacement I'm getting. So the value I'm getting, the numerical answer is correct. So the simulator explains how the spring works. Okay, if the force is applied. Now, as you can see, whenever I apply a force of 15 Newton, the spring will resist the same amount of force in the opposite direction. That is a minus 15 Newton. So the total spring length, okay, the 15 Newton of force has been applied. Now, if I keep the force constant and if I increase the stiffness, okay, if I increase the stiffness, the displacement will get reduced. Okay, as you can see, as I'm increasing the stiffness, the displacement will get reduced. Okay, at the same time, keeping the force constant, if I decrease the stiffness, okay, the displacement will be more. Okay, so if I use a less stiffer spring, the displacement will be more. If I use a more stiffer spring, the displacement will be less. So that's the condition. Now, if the force is applied in the opposite direction, instead of a tensile force, if I apply a compressive force, okay, if I use a compressive force, the compressive force will also generate the same amount of displacement. As you can see, it is also producing same amount of displacement of 0.1 meter, but in the opposite direction. So that is the only difference. Okay, so this is how the spring works. Okay, this is how the spring works. Now, let us move on. Now, this formula is applicable only when I have when I have spring in my hand. So if I apply that force in the spring and it get displaced, okay, by dividing the force by displacement, I will be getting the stiffness value. Or using these formulas, I can get the respective values. But the thing is, before manufacturing or while designing itself, if I need to find out what is the stiffness of the spring by knowing the material property and the dimensional property of the spring. Okay, so this is the formula. So K is equal to G into D power 4 divided by 8n d cube. So G is nothing but the modulus of rigidity or the shear modulus. D, small d is nothing but the wire diameter. So D power 4, so wire diameter power 4 divided by 8 into n is the number of turns in the coil. number of turns in the spring, and capital D is the mean diameter of the spring. So all this parameter represents the material property and the dimensional property of the spring. Using this, I can able to find the stiffness of the spring. So while manufacturing a spring, if I know the material property, if I know the diameter of the wire, number of turns to be turned in the spring, and the diameter of the spring also known, okay, I can able to find the stiffness of the spring. Now let us apply the condition. So G, I'm taking it as 80 gigapascal. Usually, springs are made of steel. So, steel has a modulus of rigidity of 80 gigapascal. In the general value is 80 gigapascal. So, if it is 80 gigapascal is a property. So, we convert that into Newton per meter, a constant SI unit term. So, giga means 10 power 9. So, 80 into 10 power 9. Pascal is nothing but Newton per meter square. Newton per meter square is nothing but the Pascal. So now it has been converted to SI unit. And I am taking the wire diameter as 5 millimeters. So to convert this 5 millimeters into SI unit of meters, so it is divided by 1000, which is 0.005 meters. And I am taking a number of turns of 200 turns. So it is 20 turns. The spring is coiled for 20 turns, and the diameter of the mean diameter of the spring is taken as 50 mm. So I'm going to twist the wire into a coil, and the diameter of the coil is going to be 50 mm, and to convert this into SI units, so divided by 1000, so which is 0.05 meters. Now if I apply all this value to the formula, okay, so I'm applying all this value to the formula, I'm getting the stiffness as 2500 Newton per meter. Newton per meter. Now the unit for G is Newton per meter square, as we see here, and the small d value is meters, converted to meters, and it is been power 4, so meter per 4, and denominator 8 doesn't have any unit. N is number of turns. Number of turns doesn't have any units, so turns is not an SI unit, so it doesn't have any units. And capital D, so D power cube, so it is 0.05 volt cube, so which is a unit of meter cube. So if I cancel out the units, the final unit is going to be Newton per meter square. Okay, Newton per meter. So stiffness is Newton per meter. So to increase the stiffness, okay, to increase the stiffness of the spring, okay, I need to improve the material. I need to use a strong material, so the G value will be more. Or I can increase the diameter of the wire. If the wire diameters are increased, okay, then the spring have more stiffness. And by reducing the number of turns, okay, if the number of turns in the springs are less, okay, if the number of turns in the springs are less, then the stiffness value will also be increases. And the diameter of the spring, okay, with the diameter, so this diameter, if it is lesser, okay, then we have more stiffness in the spring. Okay, the wire diameter, the coil diameter or the uh, mean diameter of the spring is it is reduced, okay, then the stiffness will be more. Okay, so based on these values, the stiffness value can be changed. Okay, so let us see the simulator how these values are governing. Okay, so in this simulator, the stiffness value, if I'm changing, okay, the number of turns is always kept constant. So number of turns is always same. So here it is number of turns are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is the number of turns. So in the simulator, always the number of turns is 12. And the mean diameter of the spring is also kept constant. So irrespective of the stiffness, here in the simulator, the mean diameter of the spring is kept constant. So the mean diameter is also constant. The material is not changing. I can't able to change the material. So material is also kept constant. So The only thing changing in the simulator is that wire diameter. As you can see here, as I'm changing the stiffness of the spring, the wire diameter is increasing. Okay, if I have more stiffer springs, to get the more stiff spring, okay, the wire diameter is more. If I decrease the stiffness of the spring, the wire diameter is less. Okay, so that explains how this formula works. So to in the simulator, since g is kept constant, n is constant, d is constant, the only value changes is the wire diameter. So if the stiffness of the spring to be increased, the wire diameter is increased. Now moving on, the springs can be kept in two configuration. One is springs in series and springs in parallel. So previously we seen only single spring. We can also combine two or three springs in either manner. Okay, either in series manner or in parallel manner. So let us discuss when the springs are in series. So when the two springs are in series, so I have a first spring and second spring. The first spring of stiffness K1 and second spring of stiffness K2. Spring constant K1 and K2, and I'm applying a force of F. As I said earlier, it's either tensile force or compressive force. Irrespective of the force, the displacement is of the system or the spring is going to be always same. So I'm here applying a tensile force. So the springs will get expanded. Okay, one end of the spring system is fixed. Okay, so entire system. So in the system, I have two springs. So both the springs are kept in series. The length of the spring is first spring is L1 and length of the second spring is L2. Okay. Now as I am applying a tensile force, now the length of each spring will get expanded. Length of the each spring will get expanded. Now the increase in the first spring length is x1 and the increase in the second spring length is x2. So now it is L1 plus x1 is the thing by the length of the second spring after deformation, and the length of the second spring after deformation is L2 plus x2. Okay, so the displacement of the first spring is x1 and displacement of the second spring is x2, the individual displacement of this. But as a total, the total displacement of the system, okay, x is nothing but is the x1 plus x2, the total displacement of the system. So previously the system is in position. Now as tensile force is applied, the springs are get expanded. The total displacement of the entire system is xs. Okay, so it's represented here. Now, though the springs are having each individual stiffness, for the entire system, okay, I can consider a single stiffness. Okay, for the entire system, I can consider single stiffness called as K system or stiffness of the system or Ks. So Ks represents the stiffness of the entire system. Stiffness of the entire system. So I need to find the stiffness of the entire system. Okay, for this applied force, and also I need to find the excess value, which is the displacement of the entire system, and I need to find the displacement of the first spring and displacement of the second spring. Okay, now I know the stiffness of the springs. Okay, I know the applied force. Now I need to find these values, xs and the ks. Ks is something the stiffness of the entire system. Xs is the displacement of the entire system. X1 and x2 are the displacement of the first spring and the second spring. Okay, now displacement is nothing but force by stiffness. We already seen that formula. Displacement is nothing but force by stiffness. So here, the displacement of the entire system is going to be force by stiffness of the entire system. At the same time, displacement of the first spring is going to be force applied on the first spring divided by the stiffness of the first spring. Okay, as the force is applied, this force is applied throughout the length of the spring. So this force in the first spring and the force in the second spring are going to be same. Okay, force in the first spring and the force in the second spring are going to be same, which is F. So that's why the displacement of the first spring is nothing but force applied on the first spring, which is F, and the displacement and the stiffness of the first spring, which is K1. Now, displacement of the second spring, x2 is nothing but force applied on the second spring, which is F, and the stiffness of the second spring, which is K2. Okay. Now we know that the total displacement of the system is nothing but x1 plus x2, displacement of first spring and displacement of second spring. So xs is nothing but x1 plus x2. So we know xs is nothing but f by ks, which is equal to f by k1 plus f by k2. Okay. If I divide the entire equation by f, f will get cancelled out. The final formula is 1 by ks is equal to 1 by k1 plus 1 by k2. If I cross multiply this formula, 1 by ks become k1 plus k2 divided by k1 into k2. So that's how we cross multiply it. Now I need ks value, so I take the inverse of the formula. So the inverse of the formula is ks is equal to k1 into k2. This become numerator, this become denominator. So k1 into k2 divided by k1 plus k2. So now this is the formula for the entire stiffness or stiffness of the entire system. Okay, stiffness of the entire system. Okay. Now, if I have three springs instead of two springs, if I have three springs, the formula is going to be k1 into k2 into k3 divided by k1 plus k2 plus k3. So whenever I add the more springs, okay, in the numerator the stiffness value get multiplied, in the denominator the stiffness value will be added. So that will provide the total stiffness of the system. So let us take an example. Okay, let us take an example. So in the example, I am taking the first spring stiffness as 200 Newton per meter, second spring stiffness as 300 Newton per meter, and the force applied is 70 Newton. Okay, I am going to use this condition and find out what is the what are the results. So now, compared to the first spring, second spring is more stiffer. Okay, as you can see, the value is having more value, so that means that it's more stiffer. So now, when I combine these two springs together uh, in a series manner, okay, the formula is going to be k1 into k2 divided by k1 plus k2. If I substitute those values here, the value is going to be 200 into 300 divided by 200 plus 300. So final value is 120 Newton per meter. 120 Newton per meter. So as you can see here, when I have two springs of more value, 200 and 300 Newton meters of stiffness value, if I combine these two springs, okay, in a series manner, okay, the total stiffness of the system become less. Okay, which is 120 Newton per meter, which is less than both the value. That means that whenever I combine two springs together, okay, the total stiffness become less. Okay, total stiffness become less, or the entire system become less stiffer. Entire system become less stiffer. Okay, so now this is the total stiffness of the spring. Okay, which is less than individual stiffness of the springs. Okay, total stiffness of the system is less than the individual stiffness of the springs. Now when I apply the force, okay, when I apply this force over this entire system, okay, I will get a displacement of force. So as we already discussed, displacement is nothing but force by stiffness. So force by the entire system stiffness. So I will be getting the entire system displacement. So the entire system displaced for a 0.583 meter. Okay, entire system displacement 0.583 meter. To find the displacement of the first spring and second spring separately, as we seen, okay, the first spring will displace about certain value and second spring will displace a certain value. Both the sum of the both the displacement is going to be the total displacement. So displacement of the first spring is nothing but the force in the first spring divided by k1. The force in the first spring is also 70 divided by stiffness of the first spring is 200, which is 0.35 meter. The displacement of the second spring is going to be force by stiffness of the second spring. So here the force is same 70 Newton, and the stiffness value is stiffness of the second spring is 300 Newton per meter. So if I find the value, so it is 0.233 meters. Okay. Now, so if I add these two values, I will be getting a total displacement of 0.583 meters. So let us check whether these results are correct. So these are numerical results. Let us check it in the simulator. So in the simulator, I am taking springs are in series, and now let me just reset these values. Now the first spring is kept at a stiffness of 200 Newton per meter, and the second spring will be of stiffness of 300 Newton per meter, and the force of 70 Newton is applied in the system. So as I'm applying a force of 70 Newton, I'm getting a displacement of 0.583 meter. So which is exactly what I get in the numerical result. Okay, and also I get the stiffness as 100. So this says that whatever I'm getting is correct, exactly correct. And also you can see that I'm applying 17 Newton of force. That force is applied in the first spring and second spring. So throughout this entire system, okay, the same force is been applied. So that's why, so here also in the first spring and second spring, I'm applying the same amount of forces here. Okay, so throughout the system, the same amount of force is being applied. So that is also been verified here. Okay, so one of the important thing you have to remember is, so whenever we combine together, whenever we combine two springs, okay, whenever we combine two or three springs in series, okay, the stiffness of the entire system become less. Okay, the stiffness of the entire system become less, or become the system become less stiffer. So if I have more number of springs, the system become less stiffer. That's a general idea. Okay, now springs in parallel. Uh, now the two springs are kept in parallel, and we are going to discuss how it is going to perform. So first, before the deformation, two springs are kept in parallel, and both ends of the springs are fixed, and both other ends of the springs are attached commonly, and the common force of F has been applied. Now both the length of the springs are going to be L. So previously it was L1, L2 because of two different springs, and the springs are kept in series. Here, both the length of the springs are kept constant or same, and both the ends of the springs are fixed together, and it has been pulled by a tensile force. I can also apply a compressive force also here. Now, if I apply a tensile force here, okay, what happens is the entire both the springs will get expanded, and as I'm attaching both the springs together, so that means that both the spring have a displacement of x. Okay, so previously it was individual displacement of springs because it is in series, whereas in this parallel condition, both the springs will get displaced at a same value. So that is x. So displacement of first spring and second spring is going to be x and x, and the total displacement of the system is also x. And the only thing is the force applied will be divided into two components. The force will be divided into two components because since they are in parallel, so it will be divided into F1 and F2. Okay, the force applied will be divided into F1 and F2. So F1 is the force applied in the first spring, and F2 is the force applied on the second spring. So based on the stiffness value, okay, the force value also changes. Okay, force value also changes. Okay, whereas the displacement of the each spring and the displacement of the system are going to be same. So displacement are going to be same. Displacement of system and displacement of first spring and displacement of second spring, all are going to be same, which is x. Okay. So as I said, I am applying a force. The force is divided into two components, F1 and F2. Force in the first spring and force in the second spring. So F1 plus F2. So for the entire system, if I apply a force of F, okay, the entire system is displaced for x. So we know the Ks is nothing but stiffness of the entire system. So formula for the force in the spring is nothing but stiffness into force is nothing but stiffness into displacement. So applying this formula here. Applying this formula here. So force is nothing but the stiffness of the entire system into displacement of the entire system, which is also x. And force in the first spring, okay, force in the first spring is nothing but the stiffness of the first spring into the displacement of the first spring. So here the displacement of the first spring is also x, and the force in the second spring, which is F2, is nothing but stiffness of the second spring into the displacement of the second spring, which is also x here. Okay, now we know F is equal to F1 plus F2. If I substitute these formulas here, so F is equal to Ks into x is equal to K1 into x plus K2 into x. Now, if I divide this entire equation by x, okay, x will get cancelled out. So the final formula is Ks is equal to K1 plus K2. So that means that whenever I connect two or three springs together, the entire system stiffness value is going to be sum of the stiffness values. Sum of the stiffness value. If I increase the number of springs to 3, so it is K1 plus K2 plus K3. As I am increasing number of springs, the stiffness value get added together. Okay, so this is the formula for the system stiffness value Okay, the entire system stiffness value. Okay, so let us find out. So I'm applying, so I'm taking the same values as we see in the previous numerical solution. So I'm applying a spring of 200 Newton and 300 Newton, and applying a force of 70 Newton force. So I'm taking two springs. So 200 Newton per meter stiffness spring, and 300 Newton per meter stiffness spring. And here previously it was kept in series condition, now it is going to be connected in a parallel condition, and a 70 Newton force has been applied. Now the total or system stiffness, the total stiffness and the system stiffness is going to be k1 plus k2 when it is kept in parallel. So 200 plus 300, which is 500. So whenever two springs are connected together in parallel condition, the total stiffness is going to be more than those individual stiffness of the springs. That means that the stiffness of the springs will the stiffness of the system will get increased when I connect the two springs in parallel. So it becomes, the entire system becomes stiffer. The entire system become stiffer. So that's how the system is going to be performing. So whenever we have two springs in parallel, so the entire system stiffness will be increased. So as we see in this formula or in the problem, as it has more stiffness. Okay, so examples are in two wheelers. Okay, we have two coil springs are attached. Okay, one outside coil spring and one inside coil spring. So in a suspension system, two coil springs are used. Okay, both are present one inside the other. So these are parallel condition. Okay, this is that's an example for the parallel condition in which the stiffness of the spring is more. Okay, as the stiffness of the spring is more, okay, the automobile suspension system can withstand more amount of force. So that's why we increase the number of we increase the stiffness of the spring by increasing the number of springs used in the suspension and kept in the parallel condition. Now the displacement, the total displacement of the system or the displacement of the each spring can be found using the formula. So x is equal to F by Ks. So F by Ks will give me the value of uh, the total stiffness value, sorry, total displacement value. So total displacement, the force by stiffness. So we know that displacement in the spring is nothing but, from the formula, displacement is nothing but force by stiffness. So here force by stiffness value. So force is 70 Newton is applied, and the total stiffness of the system is 500 Newton per meter. So the if I divide these two values, and the final value is going to be 0.14 meters. Okay, so which is going to be the displacement of the first spring and displacement of the second spring also. So the displacement of the system and the displacement of the first and second spring are all going to be same. So which is of 0.14 meters. Now, this value, x value, is comparatively more less than the uh, previous condition in which the same spring is used with the same amount of force. The only thing is these are kept in series condition, and that is kept in a parallel condition. So here the total system displacement is 0.583 meters. So here it is only 0.14 meters. So whenever we have two springs in parallel, it have more stiffness and it will have less displacement. Okay, it will have less displacement. Okay, so that's why it is used in automobile. So the wheel doesn't travel too much up and down. Okay, because of the force applied in the road. Okay, now the force applied in each spring, F1 and F2, we need to find. So F1 can be force in the spring can be found using the formula stiffness into displacement, which already seen here. Okay, so stiffness is 200 for the first spring, and the displacement in the first spring is also same, 0.14 meter. So if I multiply these two values, it is 28 newtons. For the second spring, the stiffness is 300 and the displacement is same, 0.14 meter. So the force is 42 newtons. So the 70 Newton force applied, which is divided into two components. So 28 Newton and 42 newtons. So for a less stiffer spring, for in the two springs, so 200 is less stiffer. So only less amount of force is required to make this displacement of 0.14. So that's why less amount of force is applied in the first spring. In the second spring, since it is more stiffer of 300 Newton per meter, so it requires more amount of force to produce the 0.14 meter displacement. So that's why in the second force, it has more magnitude because of the more stiffness spring. Okay, so let us check this values in the simulator. So in the simulator, I'm taking two strings in parallel, and I'm applying stiffness of 200 and 300. So I'm applying a 300 Newton per meter stiffness for second spring, and I'm applying a force of 70 Newton here. So as I'm applying the force, as you can see, displacement is 0.14 meter, which is same as the numerical result. And the force applied in the first swing is 200 Newton per meter, the purple color swing. So for that, the force applied is 28 Newton, which is exactly what I got here. And the second spring, the yellow color spring, which is of 300 per Newton per meter stiffness, which is having a applied force of 42 Newton. The 70 Newton forces in the 70 Newton force, a 42 Newton force is applied in the second spring. Since it is more stiffer, only 20 Newton of force is required for the first spring to displace it for a 0.14 meter. Okay, so if the stiffness is less in a parallel spring, okay, the force applied in the spring will be less. If the stiffness in a parallel spring is more, one of the stiffness of the spring is more, okay, then that spring will have more force applied. So more force will be applied in the second spring. So it is of 42 newtons. So this is exactly what we got in the numerical result. So these are the formulas, and these are the conditions for springs. So I hope you understand. Thank you.